Today we're going to go over the equations of a line in 3D. And there are two different ways of expressing this, and we're going to go over both of them. The first is the vector equation, and the second is the set of parametric equations, right? But both of them rely on two basic components to be able to define a line in 3D. One of them is the vector, right? Which looks like, just a direction in space, right? And the other one is some point in space, right? Some point in 3D, right? The vector has three components, right? It has three components which show which way it's pointing in three-dimensional space. And a point has three components which show where that point is located in three-dimensional space. All right, so between these two components, you can describe any line in space. Now, let's go ahead and use this to make a set of equations. And we're going to start by writing this in vector form. Okay, so say that we have this line in space, and we are given a point on the line, right, x, y, z, and we're given a vector that falls along that line, right? And that vector could be of some length, Doesn't really matter what the length of the vector is, but all that matters is that vector falls along that line, right? So we have a point, and we have a vector, and we need to describe the line. Okay, so let's call this line r of t, right? And the way that this equation is written is you have the point, right? So p naught, which would be our point, I'm going to label it down here, p naught, plus t multiplied by our vector. And since that vector kind of describes the direction of the line, we're going to call it d, right? Okay, t times d. Okay, now let's try to actually apply this to come up with a vector equation given a specific scenario. So say that we're given that p naught, some point along the line, right, is equal to 2, 5, 6, right? And that d, the vector, is equal to 1, 3, 9. All right. Now let's go ahead and come up with the vector equation. Super simple, right? R of t equals 2, 5, 6 plus t multiplied by 1, 3, 9. Now, why does the equation look this way? What is t? Well, if you think about it, right, if I have a vector, and you know how I said that it doesn't really matter what size the vector is, and I have some point in space that vector starts out at, if I apply a scalar to the vector, in this case t is a scalar that's multiplied by the vector, all that does is it just makes this vector bigger, right? Or smaller. Or if it goes negative, then it goes this way, right? Okay, so as the tip of that arrow, as I decrease or increase the size of the vector, I describe every single point along that line. So that's what t does here. T multiplies by the vector to describe any point along the line. The point, P naught, right? P naught right here. What that does is it describes the starting point. So I have my starting point and then I have my vector. And as my vector gets bigger, as t gets bigger, the end of my arrow goes somewhere along this line, right? Go ahead and draw my line here. As t gets bigger, then the end of my arrow ends up here. As it gets smaller, it goes down here, and as t goes negative, it goes down here. So it describes every point along this line. Great. Okay. So from that, another thing that we can reason is that it doesn't matter what the if I divided all of these components of the vector by 2, or by 3, or by 4, and we'll find that that's useful, and I'll give you an example where that's useful to sort of simplify things. Okay, let's say that we're given P naught equals 1, 9, 5, and we're given that, actually, let's make this something different. Let's go P naught is 2, 4, 8, and let's say that that our vector d is equal to 3, 9, 21. All right, before we even get started, what we can do is we can simplify d, right? We can simplify d down by dividing by a common denominator, and that'll just make our everything simpler as we work with this vector. So d equals 1, 3, and 7, right? Because when you think about it, we're only going to end up multiplying d by t anyway, and t is an arbitrary scalar. So d could be anything as long as the individual components are still proportional to each other. Great. Now, can I do that with p naught though? No, I cannot you might look at this and say, oh, well then I can do this with p naught, right? And no, you can't do that. The reason for that is that p naught is not multiplied by a scalar. P naught is a specific point in space, and if you divide or multiply it by it, it's going to change the point in space, right? So if we went and wrote the vector equation for this, then we would have our t equals p naught, which is 2, 4, 8 plus t times, not that, but t times the vector 1, 3, 7. Great. Now, notice that this is the exact same thing as if I were to write it like this, and I hadn't done that transformation. 3, 9, 21. This is going to be the same thing. If you gave this answer, you're still technically correct if you give this answer. However, it's not the simplest form. Okay, now that's enough for the vector equations. So let's get rid of that and let's go look at the parametric equations. All right, so the parametric equations are a set of equations that will give you the x coordinate, the y coordinate, and the z coordinate for any t value that you give, right? So x of t equals something, y of t equals something, and z of t equals something. All right, so same as before, we need our initial point and we need our vector. But the way in which we use them are different here as opposed to the vector equation. So our x coordinate is going to be our, if we look down here at the way that our point is described, we have our x naught, which is our starting point from p naught, plus t times a being the first component of our vector. All right, y is going to be y naught plus t times b. Z naught, what do you think it's going to be, right? All right, zt is equal to z naught plus t times c. All right, so we have our set of parametric equations right here. Let's go back and apply this to another problem now. So if I'm given that p naught is equal to 1, 3, 5, and that d is equal to 1, 2, 3, then my parametric set of equations is going to be x of t equals my x naught, so 1, plus t times my first component of my vector, which is 1, right? This just simplifies to 1 plus t. Great. Y of t equals y naught, which is this number right here. So 3 plus t times this number right here, 2. Z of t equals 5 plus t times 3. So there's my parametric set of equations. And you could be even asked to write it as such. You could be asked to write it as in sort of a vector format. And that could look something like this. X of t, comma, y of t, comma, z of t equals, and then it'll ask you to fill in whatever's in here. And we can do that. We just do 1 plus t, comma, 3 plus 2t, comma, 5 plus 3t. Great. And there's our parametric equations for a line in 3D space. Now let's do one more type of problem that you'll probably see. And that is, say that you're given 2 points in space and you're asked to find the line between those 2 points. We'll say that P1 is, I don't know, 3, 8, 6, and P2 is 4, 9, 1. Great. And now we have to find what the line is between these. Now, what we said that we needed was a P naught, right? Some point in space on the line. And we also need a vector. And that vector was D, right? Actually, I'm going to give D a little hat there so you can see that it's a vector. All right, so P naught is super easy. We just need to pick one of these points that we have. We're given two of them, right? We just need one. So you know what? Just for kicks, I'm going to pick the second one, right? I'm going to go 4, 9, 1. Great. Now D is a vector, and a vector that's along the line. Well, a vector has a starting point and an ending point, right? And one vector that is along the line starts at P1 and ends at P2. Now, how would we figure out what the different components of these are? Well, we would just subtract P1 from P2 in this case. So D equals P2 minus P1. All right, so let's figure that out. So each of these components, P2, so 4 minus 3 is 1. 9 minus 8 is 1. And 1 minus 6 is negative 5. All right, now we have a vector and we have a point. So it's easy from here. Let's do the parametric equations. Why not? So x of t, right, equals 4 plus 1 times t, so t. Y of t equals 9 plus 1 times t, so just t. And z of t equals 1 plus negative 5 times t. So do minus 5t. And there is the parametric set of equations. It's a horrible box. But there is the parametric set of equations for the line that goes through these 2 points. All right, I hope that this was helpful. If it was, please leave a like, leave a comment, letting me know what you'd like to see next, and possibly consider subscribing. All right, have a good one.